Okay, so let us start. So in the last lecture, we started discussing about generalization, although we did not do much. I mean, we just started. So let us try to make some progress on generalization. Hopefully, we will cover majority of generalization in today's lecture. One aspect I believe will be remaining, which is the mathematical aspect, which we will do on in our next lecture. Okay, so that is more or less the idea to talk about generalization today, cover most of the things on generalization, different tricks that can help us hopefully achieve generalization. And then one aspect which is little bit mathematical, we will leave it today and we will do it next time. Okay. So with that, let us start. So this is lecture 10, right? Okay. So we were talking about generalization. And what is generalization? In one, two, three words, how well model performs on test data. Okay. So models performance. So this basically test or tracks models performance on test data. Right? Models performance on unseen inputs, models performance on new data. I mean, all of these are kind of synonymous statements, and that is what generalization is all about. So it is basically complementary to training. In training, you see the performance on the training data, whereas in generalization, you see the performance on the test data. So there are different strategies of generalization or different strategies that tries to ensure certain aspects of generalization, right? Uh, we will talk about those, but broadly to test all of those things, what we the starting point generally is that you have data and you divide the data into train, validation and test, and for testing generalization you play with the validation and the test data, okay, or rather you play with the validation data and check the test data, okay. So broadly we divide the data set available into train, validation and test. Okay. Training data or train data is used for training, and the name itself is self explanatory, right. Validation data, you will use it for hyperparameter tuning. So parameters that you are not getting trained to parameters that are not getting trained, to tune those, you use validation data set, and lastly test data set, you report performance. So to report performance, you use the uh, test data, right. So you have this train, validation, test. Train is for training, validation is for hyperparameter tuning, and test is where you report the performance. Now in the last lecture we started talking about different reasons because of which a model might not generalize, right. uh, Overfitting was, for example, one of the prominent uh, reason. uh, so today we are going to talk about, or we are going to discuss, what are the different possible tricks are there that can potentially ensure generalization. Okay. So different tricks to uh, help is probably the correct terminology with generalization. Okay. So different tricks to help with uh, generalization. Okay. And when we talk about different tricks to help with generalization, naturally we will talk about what was the aspect that was contributing to the model not generalizing, and based on that we will come to the trick that will that potentially help us with uh, generalization, right? So first one is data augmentation. Okay. So the idea is you do not have access to enough data. Because you do not have access to enough data, if that is the scenario, then naturally your model will not learn well. It will probably miss some of the important features that it could potentially have learned if enough data, enough diverse data was there. So if you do not have enough data, one way of ensuring that the model sees enough data is to perform or is to use the trick known as data augmentation. In data augmentation, you create artificial data by uh, making small changes in your training data. You do not touch your test or validation data. So this is something you do only with your training data to potentially show your model additional features. And if you can show those additional features, hopefully the model will learn better. So what is the limitation that it addresses? Limited data. If you have enough data, data augmentation is not needed. I mean, why will you do data augmentation if you have 60,000 training data, 50,000, 20,000, 10,000? But if you have 50 data, now where are the scenarios where you will have 50, 100 data? Medical imaging. Medical imaging is one example. If you go, I mean, you have to work with maybe 100 data, which is not enough for the model to learn. So in that case, can you make this 100 as 500? If you can, potentially that is a good way. Um, that's a reasonable amount of data for the model to learn something meaningful. 100 data might not be a good number to learn anything meaningful, right? So data augmentation addresses the issue with limited data. Okay. We'll talk about data augmentation in details. I just wanted to introduce it, right? The second one is so last lecture we talked about one strategy already, which is that to reduce the complexity of the model. So what happens when the model is too complex, it can learn any function and it will potentially learn some noise. So the idea is make the model less complex. So the second trick is reduce complexity of your model. And for that we introduce the idea of bottleneck layer, right? Reduce complexity of model. So this is the second trick. Okay. The third trick, and third trick is nothing new actually. So that is done even in machine learning. I mean, all of this can potentially done in machine learning as well. So it has been observed that when a model overfits, a phenomena that happens is that the weights becomes quite large. At least some of the weights becomes quite large. So naturally, a countermeasure is to ensure that the weights do not blow up. they do not become very large. And that you ensure by what is known as weight decay. This is weight decay. And weight decay is a terminology used in deep learning. In machine learning, I will call it regularization. So L2 regularization, for example, is the standard weight decay. Okay, you can also do L1 and other things, but generally in deep learning, you don't say regularization, you say weight decay. Weight decay is nothing but regularization. Okay, and all these SGD, ADAM, this torch, all these inbuilt routines have weight decay inbuilt in them. So when you call the optimizer, you can just specify weight decay and the weight decay parameter, it will do it automatically. Okay. Weight decay, I mean also known as I said, regularization. Okay, so this is a third trick. So the first trick was for limited data. Second one was for too complex a model, reduce the complexity. So be careful with your model. Third one is for your model weights are blowing up, reduce them. Okay. Now these are three different reasons for which overfitting can happen, for which generalization might not happen. And these are three possible strategies which can help us in generalization. Fourth one, the fourth one is ensemble. Model ensemble. So here what you do is when you train a single model on the same data, the chances of overfitting increases, so generalization reduces. So the idea of ensemble is that it's the idea of bagging also, that you create subset from your data and then train separate model on those subsets. I mean the same model on different subsets can also work, and then your prediction is a mean of those models. So instead of one model, you are now potentially using an ensemble, maybe k models or n models, and your prediction is average of those models. And it has been observed that such averaging always um, improves the generalization. Okay, so ensemble, and mostly it is bagging based ensemble. There are other types of ensemble also, um, but what I am talking about here is mostly bagging kind of ensemble. Okay. Lastly, and this is the one we will not complete today. So last one is dropout. The idea of dropout originates from one limitation of ensemble, that you need to train multiple models. So that means it is expensive. Dropout allows you to train a single model, whereas while yielding two to the power m models. And what is m, what is 2 to the power m, we'll come to that later. But the idea of dropout is that you drop out, the name itself, certain units. So that means those units do not participate during training. Uh, Training means a single update, right? A single mini batch, and then you switch them here and there, and hopefully that allows the model to generalize better, because every time the model is changing a slightly, because some random units are getting dropped out. Okay, we'll talk more about it, but that is also another strategy that helps in uh, generalization. Okay, so broadly these are the five um, tricks that can help in generalization: data augmentation, reduce complexity of the model, which is the bottleneck layer, weight decay, regularization, ensembling, model averaging multiple models, and dropout. Okay, so these are broadly the five tricks. There can be other tricks also that helps with uh, generalization, right? But before we start talking about each of these separately, one disclaimer is that these are tricks. Tricks are like medicine. Medicine is only to be taken when you are sick. If you are well and fine, you should not take medicine. That might result in you getting sick. So if your model is already performing well, it does not have overfitting, you should not use any of this. This is not just something you are getting for free and you will should use it. It should be used with care, only when needed, with justification. And some of this we will start talking about today itself, like data augmentation particularly will have these issues. So these are not something that are to be used just for the sake of using. These are to be used only when needed, only when justified, justified by the data set available, justified by the problem you are trying to solve, justified by the model you are using maybe. Only then you should use it. I mean, one easy example, and let me take this example because we already talked about it last time, that bottleneck layer. If your model is not overfitting, it is performing perfectly fine, and you introduce a bottleneck layer, what are you doing? You are reducing the capacity of the model. What do you expect? If it is not, it will perform less. You want to it to perform less when it was overfitting because of this performance factor, but it was not overfitting, and you reduce the performance. I mean, makes no sense, right? So that is one example from last lecture, right? So the bottom line is we need to be careful and we need to ensure that if any of this is actually needed or they are not needed, if they're not needed, you should not use those. So that is one aspect you should be aware of, right? So these tricks are only to be used when necessary or when needed. Okay, you should not just go on and use these things. Okay, these tricks are to be used only when necessary. So this is a disclaimer I am giving before we start talking about these things in details. Any question in what we discussed till now? Yeah.
Sir, as you said, we will not be able to see if the weights are blowing up in a neural network, like exactly what's causing the overfitting or normalization of the data. So then how to submit?
Remember, I told you that you have divided your train into train, validation, and test. So first thing you should check the sign of overfitting. First thing is that the training loss is low. But thank you. You remind me one more point. There is one more point. Okay. Early stopping, I forget to mention. There is also early stopping there. But anyways, so there is training and validation, right? So this, what is overfitting? Overfitting here is, overfitting in general means that the training loss is reducing and it is almost close to zero, but the validation loss is very high. That's a classical scenario of overfitting, right? So do you really need to check the weights to see whether there is overfitting or not?
So, but we won't take. One of the reason is the weights are blowing up.
No.
Exactly if it's the
Again, you are missing the point. First thing is you need to ensure whether there is overfitting or not. Let's start from there. The first scenario can be that there is no overfitting. So if there is no overfitting, you should not use any of this, right? Now come to the second scenario. There is overfitting. And now the question is, why is there overfitting, right? Now when overfitting happens, let us go one by one. So if there is overfitting happening, right? So first thing you will go and check how much data you have. Can you check that? If you can check that data augmentation, whether it is to be done or not, can you figure it out? You can, right? Let's say there is enough data. So you decide, I'm not going to do data augmentation. Even for less data, you should not use data augmentation in certain scenarios, and I'll come to that. But for now, step one was whether there is overfitting. You decided, yes, there is overfitting. Step two is data augmentation. Should I do data augmentation? You saw that no, there is enough data, I should not do data augmentation. Then should I reduce the complexity of the model? What will you do? You will go and reduce the complexity of the model. Go and check your validation loss. Complexity has nothing to do with weights, right? So you'll go and check the validation loss. Is it improving? If it is, then you should do that. If it is not, then maybe that is not needed. Then you will go and check weight decay, add a regularizer, use weight decay, and see how the model is performing on your validation dataset. Do you really need to go and check those weights? You cannot check those weights. You don't need to check those weights. What you need to do is how the model is performing on your unseen data. You go and check your uh, on the validation data, and you see, is it performing well? No, it is not performing well. Okay, I should not do this part. The bottom line is all of these things that you are seeing are your hyperparameters. Whether to do a dropout or not, if you are doing dropout with what probability, this is your hyperparameter. What type of data augmentation to do is your hyperparameter in some sense. Reduce model complexity, it's actually architecture, right? Already a hyperparameter. Weight decay, whether to use regularized loss or unregularized loss, that's a hyperparameter. So these are all giving you a set of hyperparameters which are to be tuned based on validation data. Right? Now comes your actual question. Now it performs well. Now, if it is performing well, at that stage you can go and now say, okay, if it is performing well, why is it performing well? I want an answer. And at that stage you can go and check how the weights were before and how it is now. Because at that stage you have only one model to check the weights. Whereas while you were doing this, you had maybe 100 trials you are doing. Each one checking weights, not possible. And even then you will check some random weights here and there, right? So that's how you will do it. That's how you do hyperparameter tuning. That is basically a grid search I'm talking about. Yes, one point I missed, right? Let me write it, which is early stopping. So early stopping is, the idea is very simple, that initially your training loss will be high, your validation loss will also be high because it's random weight. As you start training, training loss starts going down. Validation loss will initially also start going down. But after a certain point, you will realize that the training loss is still going down, but the validation losses start increasing. So that is the point where you know overfitting has started. So stop your model before that happens. That's early stopping. Okay. Any other question? In case of overfitting, we have to do these in order like first. No, nothing. You have to do it based on your own knowledge of the domain. Okay. Or based on your own instinct, intuition, whatever you call it. There is no ordering like this. Okay, I gave it in this order because it came to my mind in this order. And I gave this order because this is probably the order in which I will follow now while discussing each of these aspects. So there is actually, in reality, these are not ordered. Any other question?
If you are early stopping, that means our model is already too complex. It's learning
No.
According to our data.
No.
So we can choose either of them.
No. Why early stopping means the model is too complex? Even it might mean that the function is too simple to learn, and you are making it unnecessarily complex. I mean, it is both ways, right? So no. Anyways, so early stopping I'll come anyways later, right? So yeah. Anything else? Okay, so let us start with data augmentation then. Data augmentation. Okay. So the idea of data augmentation, as I was saying earlier, is that you increase the amount of data that the model is getting trained on by creating artificial data. Okay. Create artificial training data um, for the model to learn from. You create artificial training data for the model to learn from, right? Now, how will you create artificial data? There are different ways of creating artificial data. So let me write it down. And I'll only and again the list is not going to be exhaustive. The list is not going to be in some order of preference. It is just going to yeah, you list down certain things, ways of um, data augmentation. Now, before I start talking about ways of data augmentation, one thing that you should keep in mind is that data augmentation strategy is a function of your data modality, problem, data type sometime, I mean, and so on and so forth, right? So it is not a one rule fits everything. Each one will have different rule. For example, there is certain data augmentation strategy that you will use for an image kind of data, but you should not use it for time series or a sequence data, and vice versa. And there will be some which you can use in both cases. So that is data modality. Second, some data augmentation strategy should not be used for certain problems because it changes the meaning of the problem. So, and you will see, when I give the example, it will become quite easy to follow actually. So that means it is also problem dependent. Okay. So ways of data augmentation, right? So the most obvious ones, most used one probably are, the first one is translation. Okay. Second one is rotation. And these are all I am writing, mostly you will see that are for images. I will write for sequence later. Okay. Third one is clipping. Fourth one is jitter, jittering. You can say jitter, double T actually. Okay, jitter. And then there are others also I am not writing, but these four are kind of common, I'll say. Okay. So what is translation? There is okay. One more is important. Let me write scaling. Scaling. Okay. Remember last lecture I talked about this MNIST data set. So I'll give this example because this is image, right? So on based on MNIST data set only. Translation, right? Suppose in my training data, I have a 5 which looks like this, okay, which is at the middle of the image. Translation means I can translate it and make it to the right, left corner, right corner, and all of this. So I will create additional data. So create data by translating this 5. So maybe your 5 now looks something like, and the reason for this kind of data augmentation is that, remember the example I gave last time, that if same pixel location it is memorizing that this pixel location being black means it's a 5 or 9, whatever I wrote, I forgot, right? This will ensure that never happens. By translating, it will actually learn that when this thing is there, it's 5 and not some random pixel being 1 or 0, right? So this is translation, where you translate your image left, right, up, top, bottom corner, right corner, and you create additional data. So the green one was the data that was not available to you in the training. The pink one was the one that was available. The green one you created artificially by using the pink one where you translated this 5. So you get one additional data. Now you can translate in different ways. You can translate each data in different ways, and that can help you augment your data. Clear what is data translating? Next is rotation. So the original data was again like this. Now as human, we should be able to identify that this is also 5, right? If I rotate it by a certain angle this way, that way, even if I rotate it by 90-degree angle, I mean, as human, we will be able to identify it's a 5. So the machine should also be able to identify it's a 5. So even rotating by 90 degree, let's say, that still remains a 5. but that's a very unlikely thing you will encounter during the training data, during testing. But slight rotation you will definitely encounter, right? Some people, there are many who write cursive, right? So they write at an angle and both side. So you know how much to rotate based on those observations, right? So how much to rotate is for you to decide, but to rotate and augment data is a logical choice, right? Third one is flipping. Flipping means mirror image. So this was my data. In some cases, not in all cases, I will say. I mean, this might also be helpful. Sorry, I did not flip it. In some cases, for example, if I know I'm only dealing with uh, uh, numbers, in that cases, this might not be useful because no one will write 5 like that. But there are certain scenarios where flipping does help, where because the okay, but again, not so common in handwriting, for example. The rotation and translations are very common in handwriting. Flipping might not be so common. Okay, but for example, I'll give you one example, right? I mean, when you see this YouTube videos, right? Uh, sometime they put these shots which are actually flipped. So right becomes left and all of those things. So house, for example, if you flip the house, it still remains a house. Instead of entering from the left, you will enter from the right. So in those kind of scenarios, flipping is useful. Okay. Mirror image, yeah, exactly. Mirror image. Right? Fourth one, and this is actually really helpful, is jitter. Jitter means you manually add a certain amount of noise in your data. So jitter, a very small amount of noise, so that so it will look like this in this case. So I have this 5 again, right? So if I add jitter, 5 will be 5, and because I have added noise, some noisy pixels will come up like this, right? Now, as human, if I get some noisy things like this, I will be able to identify it's a 5. So the machine should also be able to identify it's a 5. But for the machine to identify it's a 5, you need to provide it with data where it is actually noisy. So in the training data, what you do is you added noise, so that's jitter. So basically, some pixels you randomly select and make 0 as 1. Okay. So pixel flipping, or yeah, I mean, you flip pixels also, I mean, you can call it, right? Last one is scaling, and this is also very common. Okay. What you do is that you enlarge the portion and only take that. Some people write in small, some people write in larger font, right? So the model should be able to detect those as well. So this is scaling. Cropping, this is in some sense cropping also. Okay, I cropped it, but I made the image size same. So the portion I'm focusing on, that will get enlarged. So it's scaling, you are right. But in some sense, when I'm doing that, the side portions which are unnecessary, I am cropping. But cropping is also there. I mean, I might not enlarge it, I can just crop it. That's fine. There are unnecessary features that are there that might confuse my model. I'll remove it. So as I said, this is not like everything possible. These are some ideas I am giving so that you can come up with your own idea, and cropping is absolutely fine. Okay. Now, let us see when these are not useful. Now, in the physical world, right? Okay. Um, suppose I am giving a robot a task. Okay. The robot can see this thing. Okay. And I'm saying pick up the object that is closest to the remote. Okay. What is closest to the remote? The pen I kept closest to the remote, so it should take it. That's the job I have given to my robot, right? And that's the job I want to give to my robot. Now, in the process of training the robot or somewhere, right? If I translate it, it will no longer be closest. So that means you have to understand the problem first before using this. And this will become even more obvious when you start doing mechanics problem, when you start applying it to real world problem. In real world, translation means translation. The model should not be translation invariant. The model should understand translation in real physical world. So in real world problems, for example, let's say uh, practical one problem, right? It is not translation invariant. If you're doing data augmentation using translation, that is wrong. You should not do it, right? So you have to be careful that for your model, does generating additional data by doing some translation is meaningful or not? Or is it changing the whole idea of physics itself? Because if it is, then you should not do it, because then you are generating some artificial wrong data, because your label will not be same. Remember, we are only changing the x, and we are saying this change in x will not change my y. But if the change in x changes my y, then that's not a proper data augmentation, because this change y you will not know. So the idea is data augmentation you can only do when changing x does not change y. Then only it will give you an additional row in your training data. But if your change in x changes your y and this y is unknown, then you cannot, that's not data augmentation. And if you don't change it, whereas it should have changed, then that's a wrong data augmentation. So you need to be aware of that. You need to understand the domain you are working in, and only then you can do a meaningful data augmentation. Rotation. This one was looking perfectly well, right? Rotating. Take a 6 and rotate it 180 degree. It will become a 9, right? So even in letters, numbers, you cannot use rotation without caution. Same for flipping, 6, 9, again, same thing will happen. So flipping and rotation, definitely for 6, it will not work. Um, it can also might not work if you are writing 3 where the space is very small. Like if you write 3 like this, that's a 3, right? But if I rotate it, the model might understand that I missed something, and that's why it's a 8, although it's not a 8. So flipping should not happen in this kind of data. So you need to study your data before you decide to use any of these ideas, right? If you use any of these ideas without um, understanding your data, then that's a problematic thing. For example, scaling, tumor detection. You had a small tumor, to scale it. I mean, what is this? I mean, you should not do it, right? So it's very domain specific, right? It's very domain specific is what I want you to take home. That's the take home message. That this data augmentation is to be used very carefully. It's domain specific. You should use the knowledge of the domain to use data augmentation. And without the domain knowledge, if you don't have domain knowledge, don't use data augmentation. If you're using data augmentation without domain knowledge, I mean, that's a blunder. It's better not to do data augmentation and have a less accurate result. Okay. So data augmentation is to be approached with care. Okay, it's not something you should approach blindly, and that's a recipe for disaster. Now this was for images, right? I said I will also talk about data augmentation for time series. So for time series, some popular strategies include, and again, this is not exhaustive, these are just some of the popular strategies. Okay. So the number one is, let's say, window slicing, which is actually like the cropping in image. In image, you crop the image. Here you make it small window, and some of the windows you remove. So window slicing. Then window permuting. So you create small window and then permute their location. That's also done. But again, window permuting is a very risky thing. I mean, if it is changing the meaning of your data, you should not do it. I mean, language, you should not do window permuting. I mean, I am and am I does not mean the same thing. Okay, so you should not do. So again, same message remains the same, that one needs to be very careful. Third one is very common, which is again jitter. And this one actually is kind of universal. You add a small amount of noise to your data at each pixel location, and that is what you do. Fourth one is scaling, again same as before. Okay. Fifth one, flipping also works sometimes. Again, very risky. Should be used with extreme care. Can change the meaning as a whole, and so on and so forth. Okay. So window slicing. What does it have? What happens? So suppose I have a data which is like this. In window slicing, I will maybe this portion and this portion I slice out. So what I am left with is the remaining data. Okay. So this is window slicing. Window permuting, this is funny. So let's say my data is this one. I create two windows. This one is one window, this one is one window. Okay. So this is window 1, this is window 2. I permute 2 and 1. What will happen? So it will start with 2, then the middle portion will come, and then 1 will come. So basically this will go here, this will go here, and whatever you get is your, yeah. So it is what? Something like this, and then suddenly it will go up, and then suddenly it will probably go down or up, I don't know. I basically switch the position of the two, 1 and 2. So this is window permuting. Jitter is simple, add noise. So let's say my image was this, sorry, my time series was this. After jitter, it will become so you have added small noise at every portion. So it is now following the same path, but with a small noise. What is the next one? Scaling, simple. Scaling and flipping are actually simple. Okay. So scaling. So suppose this was my thing. I scale it up, and different portions can have different scaling, by the way. So when I scale it up, maybe it looks like, so this, so it's the second peak I have scaled down, the first peak I have scaled up. Clear? Huh. Yes, so this you are right that for a time series data, the sense of causality is lost in that case. Correct. Correct. So this is only useful when the history factor is not there in that data, or the history factor is not important for your classification part. So in that case, for example, think about speech. Now in speech, if someone is happy, the pitch goes up. So it's only the pitch that is of importance. And in happiness, whatever he or she is saying might not make sense also. But the pitch being up is the only feature you are interested in. So in that case, additional switching actually changes the meaning of the sentence, but that's not what you're looking at. You're looking at the pitch, and from the pitch, you are trying to sense the emotion. But for in a normal physical sense, this you should not never use. I mean, in a weather prediction, if you're using this, I mean, then good luck. I mean, this is sequence data. Need not be not okay. I wrote time series only, right? Yeah. So this is sequence actually. Time series is a special type of sequence, but not all time series are sequence, right? You're right. I mean, we use the term sequence, not time series. I sometimes write time series by practice because of my background, but yeah, it's actually sequence. And time series is a sequence, but time series is not the only sequence. Okay. No, because time series is a sequence, and time series continuity is needed. Similarly, there are other sequences also where time series where continuity will be needed, but there it's not about whether the data requires continuity or not. It is about what you are trying to predict. Does that rely on the continuity of the data or not? Two are different things. One is, are you exploiting the fact, or are you exploiting the continuity to make your prediction? If the answer to that is yes, then you should not do this. But if you are processing the whole data and based on some other features like pitch, I was saying, right? You are taking a your model is making prediction, then you do it. So the message remains the same. You have to be careful for before using this. I mean, it does not change. Flipping, and this one will be again the same question will come. See, in flipping, what you do? Your time series is like this. You flip it. Now, for image, flipping was making sense. For time series or sequence, how does it make sense? For time series data, this will not make sense, right? But it's about the peaks, for example, let's say. If it is about the peak and both either direction, and it's the magnitude that only matters, then it will start making sense. Okay, so these are again some strategies for, yeah, I'm coming. So these are some strategies for data augmentation sequence. This I will say is even more sensitive than the image ones. Image ones are still more generic. This one you have to be even more careful for using this, and that is kind of obvious, I will say, from anyone who has seen any time series data. Yes. No, data segmentation is the output of the model. So in data segmentation or segmentation task, segmentation is a task that machine learning does where it segments certain portion. So for example, I'm giving it an image of this classroom and saying uh, which one is Kasip, let's say. So it should create a box around you, for example. That's segmentation in some sense. It is this is cropping. I mean, this is slicing. This is not that. And repeat it. That's also done. That is another strategy. Yes, this is not again. This is what you are doing is, if I understand correctly, what you are saying is that let's say I have 5 seconds of data. I repeat it 5 number of times, so I get 25 seconds of data. That's what you are saying, right? Correct. So you are repeating the cycle, right? This you can do if you know your data is periodic, cyclic. So you can do it. If you know your data is periodic, you know it is going to repeat, get it to repeated. If that knowledge is there, this is a valid way of doing it. The model will, it's very simple, right? As a human, you are there, and let's say one more student, take anyone, right? You met them first time, you said your name, he's introduced himself, and then after 10 days, will you remember his name? No. But if you start talking every day, after 10 days, you will remember his name. So it's about the model seeing the same thing again and again. That's also important. So when you're doing it, it is seeing the same thing after a certain interval again and again, and it is learning that the model is periodic. The data is period, not the model. The data is periodic. The data is periodic, you know. How the model knows it is periodic? It does not. By doing this, you are letting it know that, okay, see, based on the data, you can now learn actually it is periodic. Right? Yeah, so that is another strategy, by the way. I'm not writing it, but as I said, this is not exhaustive. That is another strategy. If the data is periodic, you repeat it, and you get longer data, right? Yes. Correct. That's what I'm going to. That if you know it is periodic, the data, then take a periodic activation or something like that. Then it's not a challenge. But if you know that it is not periodic, then you should not take activation. Or if you have some sense it might be periodic, but it might not always be periodic, then you do data augmentation. Because sign activation or periodic activation means it is always periodic, which might not be the case. For certain initial condition, it might be periodic. For certain other, it might not be periodic. So by data augmentation, for those initial condition, you can actually let the model learn that, okay, this initial condition was periodic, this was not periodic. Okay, but so hopefully it will learn, but yes, because of activation function, it will have some challenges. Yes, exactly. Yes, so it will violate, but the idea is that hopefully you are not trying to extrapolate in time. Or not that much in time, right? Okay. Or the other option is use a combination of activation functions with learnable parameter alpha 1 and alpha 2, and the activation function is alpha times 1 times activation 1 plus alpha 2, and alpha 1 and alpha 2 are function of your input. So then it will activate which activation function is needed based on. So that's another post. Okay. I think battery ended, right? Okay. Any other question? So, in general, from this discussion until now, I hope you are able to appreciate that it's a good trick, but it's a risky trick, and you should use it with care. I'll give you one last example why it is risky. For example, with the flipping case, and the course is deep learning for mechanics. I've not done any mechanics, so let me take one mechanics example. At least to respect the mechanics part. Although the practical data set was quite mechanics also. So let us take, and this is something all of you will probably be able to understand. You don't need, yeah. So this is a beam, okay, simply supported beam we call it, applied to certain load, okay. This beam is made up of concrete, reinforced concrete cement, RCC is what, anyone civil engineering? No, okay. So it is made up of RCC, reinforcement concrete, okay. And because it is RCC, if I look at the cross section, it will look something like this. The pink ones are your steel bar, the reinforcements, and they are generally put in the bottom of the cross section. Why is it put at the bottom of the cross section? Because concrete in general is weak in tension and strong in compression. So in tension it fails very quickly, in compression it can withstand load. Now why at the bottom? Because of this loading scenario, it will deform. If I look at the cross section will deform something like this. Because of the load is coming from top, right? So the top portion is getting compressed. The bottom one is getting stressed or tensile. Stressed anyways is coming, but tensile kind of behavior. Now, because of the bottom being tensile, what will happen? It will fail, weak in tension. So by giving this reinforcements, you are letting the reinforcement carry that load, and still is good intention. So as a result, it will not fail. Clear? Now in practice, you will not have this diagram on the right. In practice, you will have this loading diagram. I mean the left one, the black one. This is what will be given to you. And let's say you are asked to find the failure load. Okay, input is what? Let's say load, magnitude of load, direction of load, or let's say just magnitude of load, right? And your failure is, or your output is failure load, or failure happens or not. Okay, does it fails or not? Now the same load, if I flip it and I say, okay, this is fine, but even for this, the behavior will remain same. Physically, that is wrong, because as soon as I give this green load, the deformation pattern will now be tensile at top, compressive at bottom. Concrete is weak in tension, so it will fail at a much lower load, right? Now this is the actual problem, right? I mean, these are done in this, there are beams here actually. This four side, you will find beams. So if this, now you want to use AI for this problems, and you don't have enough data because you cannot actually break beams and collect data. You said, okay, I'll do data flipping. So then we might die. It might fall on our head. So again, physical problem, you have to be careful. Don't just do blindly, is the message, right? Because flipping might change the whole meaning. Okay, make sense? Okay. So now let us go to the other portions. I forgot what are the others. Reduce complexity we have already covered. I'm not going to repeat it. I mean, it is basically that bottleneck layer we talked about. So same thing. Weight decay. Weight decay also we have talked about. Remember when? Yes, when? Automatic differentiation. Back propagation, I was taking that thing, right? So we have not talked about it seriously or dedicatedly, but in the back propagation example, I did take those weight decay part, but let me write it again. Right? So the next one is weight decay, which is basically regularization. So here the idea is that weights are observed to blow up. The weights are observed to blow up when uh, overfitting happens. Okay. So if I reverse this argument, one way to avoid overfitting is to make the weights not blow up, is to stop the weights from becoming very large. So this means stopping the weights from getting large can potentially stop overfitting. Okay. So now how do you ensure, now I'm afraid of this. This is really big. Oh, okay, it has gone back to the back. Hopefully it will sit down. Okay, great. so, so one thing that we should do is that we should somehow try to force the model so that it does not allow the weights to get really big. Okay. So how do you do that? One option is that in the loss itself, you add one additional term which penalizes the loss whenever the weights become very large, right? So add an extra term in the loss. Okay. So, if I take the mean square loss, mostly I have been taking that. So, L, right, let us say your it is your mean square loss, let us say. So, MSE loss, let us say, plus you add one additional term, which is this one. What is theta? The parameters of your neural network that you are training from training for. Now, in this, what will happen if the theta becomes large? Your loss becomes large. So, during the optimization, the model will try to minimize MSE with smaller thetas. So, it will try to find smaller theta that minimizes the MSE. So, it will not become large. And this is a classical scenario of regularization, right? And this is what weight decay is also. This is weight decay, and this lambda parameter is known as the weight decay parameter or decay parameter. Okay, so when you write weight decay is equal to 1e minus 3, this lambda is what you are basically specifying to the model, to your optimizer. Okay, so this penalizes when theta becomes large. This is basic in, I mean, this is L2 regularization, obviously. We call it, in normal machine learning, I would have called it L2 regularization. L2 because I am taking the L2 norm, which is theta 2, right, which is like sum of square. So, this means basically theta 1 square plus theta 2 square plus theta 3 square plus dot 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 theta k square, let us say. In deep learning, it is called known as weight decay. Okay. This lambda parameter, let me write here. So, lambda in machine learning, I will call it regularization parameter, right. Just a parameter, and it is actually an hyperparameter, right. It is another hyperparameter. Here we call it weight decay parameter or weight decay parameter. Okay, and the good value is, I know, 1e minus 3, 1e minus 2, 1e minus 4. Generally, in that range, you set the value of lambda, because you don't want to make lambda too high. What will happen if lambda is too high? It will only focus on the weights and try to reduce it. Whereas if lambda is very small, then the weights can blow up. So you need a balance in the two. So 1e minus 3 is a reasonable number, but it's a hyperparameter, you should tune it. Now, this L2 regularization is not the only regularization. You also have, for example, L1 regularization, where you take the mod of theta and add it up, right? So, let me draw it here. So, L2 regularization, if I have to plot, it will look something like this. Parabolic square, right? L1, if I plot, I mean, it is symmetric. I mean, don't go by my drawing, but it's symmetric on both sides. And yeah, I mean, ideally the origin should be here actually. Okay. So basically, the green one is, sorry, the green one is L2, the black one is L1, and there is also L0, by the way. L0 is even more strict. It will push everything towards 0. Okay, L1 pushes more towards 0 than L2. L0 pushes many towards 0. So there have been work where they have used L0 in neural network to come up with expression that you can, so very compressed kind of expression, like exponential of something something. Okay, which then you can just put it in, deploy it directly. There is nothing there now to deploy. It's just an expression that you deploy and it is very fast. There have been work where they have, I mean, people have, researchers have used L0 also. But broadly speaking, L2 is what is used in deep learning. And L2 is used in deep learning because it's well posed, differentiable, easy to handle, and so on and so forth. Louder. Faster convergence might be debated, but anyways. Okay. It is not convex in terms of I mean, it's non-linear neural network. MSE is already uh, non-convex when the neural network is sitting inside MSE. So it's not convex.
So, why don't we go like on the left, on the right side, like L3, L4?
Good question. You can. I don't think anyone is stopping you. But the idea is that if you go to L3, L4, L5 or higher, right? There is L infinite also technically. If you go there, so already L1 and L2 you start, you prefer L1. So you are already preferring L1, you are going to L2 because it is differentiable at all points. So already, but if L1, L2 both were differentiable at all points, we would have preferred L1. So L2 has already addressed the limitation of L1, and L2 after that do not have a limitation that L3 can address. L1 can address, so we go L1, but L3 I don't, there is nothing, so that's why. Same purpose. So it has nothing more that L4 can serve that L2 cannot. But L1 cannot serve, for example, L1 is not differentiable at that point, right? So, but L1 is quite good actually. Okay, so this was the third thing I think. So I'm going back because I forgot what are the things I wrote. Ensemble, early stopping and dropout. Dropout we will not do today. Let's do early stopping first. Early stopping, right? So early stopping, the idea is, broadly speaking, stop training before model overfits. I mean, it's very simple sentence. This is what it is. You should stop training before the model starts overfitting, right? But how do you know the model is overfitting? Only from training you cannot know. So to see whether the model is overfitting or not, you need to test your on your validation as well. So naturally what you do is for per iteration or per epoch, whatever you are plotting, you plot both your training loss and your validation loss and see how they are behaving. And from there you will get an idea that when it's starting to overfit. Although it's not very straightforward to understand also because of the, I mean, if you have trained a model, so you know, sorry, you know it's quite jittery kind of training with Adam because of this mini batch and all of those things. So, but so you need to observe the history a little bit to understand this phenomena, but let me try to draw. So let's say the training loss, let's start with the training loss, right? Let's say training loss is something like this. This is the training loss, okay? It looks something like this, right? There is jumps and all of those things that you observe. Let's draw the validation loss. This is what you will probably find in validation loss. I mean, not exactly, but this is a potential way, right? Now, if I have to early stop, I can see two places where I can early stop. I mean, the earliest stop will be here because after this, I see no improvement. If you want to be little bit, you want to try out little more, then maybe here. Okay, that's also early stopping. Beyond that, it is clear overfitting. And in between, you can see that it is not really learning much. It almost straightened up. There is some jump, fall, but that is like luck, I will say. Okay, so these are the two portions where you can early stop. It's your choice which one you want to select. Um, but yeah, so early stopping means you don't need them. You stop when the validation loss has saturated or starts increasing. So early stopping is decided based on validation loss because it's also a hyperparameter when to early stop. Clear what is early stopping? The next one is ensemble. I have 5 minutes, should be enough. Ensemble. Bagging. So here the idea is that a single model trained on all the training data has a larger or has a higher probability of overfitting than a single model or multiple model trained on subset of the data. Okay. A single model trained on all training data has higher probability of overfitting. Okay. So this is the motivation, and because of this motivation, the solution is train multiple models, and then from here output is equal to average of this model. Output is equal to mean prediction. So each of the model will give you a prediction. Take the average of those. Okay. Clear? Okay. Okay. So what do you do? So this is the motivation. So what do we do? Let us see. What we do is as follows. So what we do is create k. I mean k is probably not the right choice. Let's call create p random subsets from training data. So although you have a big training data, you create p random subset of those training data. There might be some overlap also. I mean, it's fine. Okay, so some data might get repeated in multiple model, and that's absolutely fine. And then for each subset, you train the model. So how many model you will get? P. Each subset you train the model. So P subset you get P models now. The model architecture remains the same. Nothing is changing. We're just training it on these subsets separately. So train neural network on each of the subset to obtain P models. Each, and these are P models because theta is different for each of this. So you have P different thetas now, right? Or set of thetas. And then once you have this, then it's simple. Predict using P models and take average. And it has been observed that such a model trained based on ensembling are generally generalized better. And the reason is, even if one model is kind of getting overfitting, the others are kind of balancing it out. So in that sense, so the generalization improves when you do this kind of thing. The problem, however, is that you have to train now p times, so your computational cost increases. So the advantage is that this results in better generalization, right? However, it's expensive as multiple models are to be trained. And we'll start from this point in the next lecture, that it's expensive, and we'll see that how dropout addresses this, and then we'll do some maths on dropout. Dropout has some mathematical proofs that we want actually, which we will do. Okay, so I'll stop here. Next lecture we'll start from this limitation and talk about uh, dropout. Dropout we did not cover today. And once dropout is done, we are ready to start CNN. So I'm not sure if CNN will be able to go down.
Instead of one big model, can you not train like
You can.
10 a bit simple model?
You can.
Yeah.
Yeah, then that will not be called bagging. It's still an ensemble model, but bagging terminology is when the model is sent. Okay, but it's ensemble. In fact, you can do the one neural network, one GP, one that also you can do. I mean, that's fine. Okay. Okay then. Thank you.